Any questions from the previous lecture on this topic? No?
I have a question, Professor.
Yes, go ahead, please.
The Kn coefficient.
Which one?
The Kn coefficient for.
Yeah, the K coefficient. Yeah.
So why have we already considered only 3 modes of vibration? Like there can be n modes of vibration.
Because usually when you have any vibrating system, the final vibration is going to be a combination of all the modes. So in the same time that this mode here is going to be happening, also some of this mode number 2 is also going to be happening. So just imagine that mode 1, the pure mode 1, is going to happen when the entire beam is just going to be coming up and down like this, right? It's going to be going like this, up and down, right? In the same time, while it's going up and down, also a little bit of mode 2 is going to happen. And we call this the participation factor. If you recall this item or this term, participation factor, yes or no?
Yes. Yeah.
Okay, all right. So this is also one of the things that's going to be happening, that you have combination of all modes is going to happen at the same time. So the final vibration is going to include lots of other modes. But heavily, it's going to be mode 1. So mode 1 is going to be like the control one that you can see with your eye. And maybe combination of 1 and 2 and 3, maybe fourth mode also is going to happen. So you're going to feel it that in the same time, while the beam is just going up and down, also a little bit of mode 2 is happening. So you see here, the final case, unfortunately, it is tough to draw it here for you, but I will do my best. So let's say beam is going to be coming like this mode 1, and the same time it's going to be doing this. And here is going to be right in the middle, and then continue this way. I'm exaggerating here, right? For this deformation. This deformation is going to be very small. So something like this is going to be also happening, if this makes sense to you. Or maybe something like this, and also something like this. Let's say this is going to be going down, it's going to be going up. So this point is going to be right here in the middle, right? And this point is going to be like this. So what I'm drawing here is combination of mode 1 and mode 2. If this makes sense to you. Mode 1 is going to be just like this solid line. At the same time, mode 2 is going to be happening. And mode 2 means that this piece is going to be going up and this piece is going to be coming down like this. Okay?
Yeah. So another way we could think about is like when we do the mode analysis and we consider like the top 90% modes that contribute to the structure.
Yeah.
And that's why we consider the top 3.
Yes. And also part 3 also is going to be there, but let's say 90% is going to be coming from mode number 1, right?
Yeah.
Roughly. And maybe 3% coming from mode number 2. Maybe 1% is coming from number 3. Then you have lots of other little bit of fractions of the higher modes that you don't really care about because not really affecting the performance. So in a case like this, I'm going to say maybe mode 1 and mode 2 is going to be the main, I'm going to say here, impacted modes, if you like. The rest of the modes is going to be very small. Just so you guys know, I uploaded new set here of this floor vibration. So if you like, you can download it for quick. I added one slide. It's going to be useful during our discussion. I thought it's going to be useful instead of showing you an outside detail out of this slide set. You can just add it here to the slide set. It's going to be useful to you. So we discuss this issue, and then we say the frequency for a beam or a system can be determined with this equation here. This after Allen and Murray, which they develop here. These people here, they develop this research report that we're going to be looking into. And you just say, if you know deflection of the beam under sustained loads, all what you need to do to find out the frequency of it, you're going to say F sub n equals 0.18 square root of G over delta. Why do we say sustained load? Why don't we do here deflection for live load? You guys have an answer for me? Anyone can help me with this?
We do it for sustained load because live load can change as compared to time. For example, if it's an office building, there will be live load in it most of the time during the day. But at night, if there is no one, there will be almost zero life load.
Okay, so this delta here, or this deflection, is going to be for sustained load, which means a permanent load. Am I correct, Mahim?
Yes, sir.
So why I'm using here, what is the reason that I'm using the dead load deflection and not like the life load deflection?
Because dead load will be over there on the time, which will cause this frequency, or which will cause the floor to vibrate.
Is it because it's dead load deflection, or because the dead load deflection is related to the mass? Because look at this, it's about the mass, right?
Yes, sir.
And you know from dynamic analysis that you need to have the mass and the stiffness. So the stiffness, I understand, is giving the deflection, and the stiffness give deflection and the dead load deflection. So they call it here sustained load. Thank you. So I added this here to the slide, some G values, just in case if you guys are not familiar with it, so at least you have it handy. Different units. Added a little bit more arrows to this graph, so you know exactly which one is for what. And then we said if you like to do here combined effect between girders and between beams, or here it's called a joist. This gave you sub J for the beam, and here J is given for the beam, which is joist, and G is given for the girder. We should be able to figure out the combined frequency. If you like to do here the combined mode between girder panel and joist panel here is going to be like the beam panel. What you need to do is to combine the deflection in this fashion to find out the frequency of the entire system. And then we said here in chapter 4, we're going to have these limits, and I guess this limits is going to be the same as the chart that we were just looking at, this chart here, just given here in a table format. And it says here the maximum acceleration, which is the actual acceleration or the demand acceleration, in terms of G's as a fraction of G, AP divided by G. You can determine it by using this equation here. This is what the design guide says. I'm not going to say here the code, because actually vibration is not part of the code. Vibration is like an additional thing that you do to structures to satisfy certain requirements, which is the feeling of people when they are walking on a facility that they don't feel that the entire system here is vibrating, and they're going to be feeling a little bit scared. It says here is going to be equal to P sub 0, e to the negative 0.35 frequency of n, and of course it depends. If you just have beams, you do it for beams. If you have beams and girders, most likely you're going to be doing the combined effect between beams and girders. You take this divided by beta. Beta now is going to be the damping ratio, combined damping ratio from all sources that you have, and then divide by the weight. And also this weight is going to be the weight of the panel. We have also combined weight. So if you have just joist, like beams only, you're going to be doing this for the beams only. If you have beams and girders, maybe you need to find this combined for both of them. Here's the equation again. We understand that P sub 0 is going to be constant. So this is going to be real simple equation here that you need to run through. The problem is, how much is this W? How can you figure it out? And this F sub n. Because look at the equation, AP divided by G. This can be one number that you need to figure out. It doesn't mean that you need A sub P only. No, you need A sub P divided by G as one factor. And this is actually what you're going to be comparing with the limit. And the limit is simple. We're going to say office building is going to be half percent. So now you're done with the limit. The problem is how much is the demand that you have in there. P sub 0 is constant. 0.35 also, it's just a number. Beta is simple. So the real tough issue here is going to be F sub n and W. This here represents the mass, and this here represents the frequency. So, okay, damping ratio. How do you do here damping ratio? It's going to be simple. It's going to be based on this table. We say for any structure system, you just add here 1% for the beta. It's going to be 0.01, or you call it also 1%. If you have ceiling and duct, let's say in an office building, it's going to be 1%. Lots of offices now, they don't have a ceiling. So if you know that no ceiling is going to be installed, so you don't really need to include this. If you want to, it's going to be up to you. but you know that you're going to have lots of mechanical ducts and wiring and cables, so you can just go ahead and use it if you want to. If you have lots of computers and no paper fit out, so in this case, you can just use here 0.5%. If you have lots of partitions, you can use somewhere between 2% to 5%, which makes big difference here. Because look at this, you just look at the structure system, it's gonna be 1%. And just for the full height drywall partitions, it's gonna be 2%. So it's gonna be a big source. And now look at the equation back again. You have here this relationship, direct relationship between beta and between AP over G. So when you double this value here, you cut this into half. So it's going to be really sensitive. So you got to be careful on the beta factor that you pick and choose.
Professor, I have
Yes.
a question.
Yes.
In the slide, you said that the value of PO is 65 pounds. Where did you get the 65 pounds from?
Oh, this is given. This is based on this analysis and this is study and just given in the design guidelines. So it's like a constant.
So it will always be 65 pounds, or will it only be 65 pounds for low frequency building floors?
It means here that this weight that you're considering here in this equation, don't forget that this P sub 0 here, it may also include other factors. So when it says here 65 pounds, it doesn't mean that the weight only is going to be 65 pounds. It's going to be that weight, right? It's going to be causing this vibration that you like compared with this limit. So for example, if you have a very light person compared to a heavier person, you cannot say, I'm going to change this P sub 0 because now I'm going to have a heavier person. Like a regular person is going to be at least 200 pounds. And then you say, no, this P sub 0, 65 pounds is not good. No, it doesn't work this way. In this study and based on this analysis, this is going to be the P sub 0 that you need to use in here. So this is like a constant, considered to be a constant here.
Okay.
Okay. Now here's the tricky part. How would you find out this panel weight, W? As I said here, I'm gonna have here two tough items that I need to work with. It's gonna be F sub n and W. Because P sub 0 is constant, this is just a number, constant, and beta is simple. I can just figure it out from here. So the problem is gonna be F sub n and the W, the panel weight. This is gonna be the problem. Panel weight, generally speaking, is gonna be equal to some uniform weight that we need to come up with. It's gonna be the supported uniform weight multiplied by length by width. Length of what? Of the panel. I'm not clear to me what is the effective panel width. Is it like the girder length? Not sure yet. How about the L, the member span? Is it just the member span? Not sure yet. It says here for beams or joist, I'm gonna have this P sub j, which means effective width for the beam panel. So now I'm gonna be working on the beam panel. Now, let's be careful here. Beam panel width. I'm not gonna say it's gonna be equal to the girder length because the girder is supporting few beams parallel to each other. So this B sub j, effective width for the panel, which panel? The beam panel, is gonna be equal to some factor, a constant, multiplied by D sub S, which is transform moment of inertia of the slab. So this is gonna be D sub S. It's gonna be something about the stiffness, which means moment of inertia. So D here is used as moment of inertia of the slab divided by moment of inertia of the beam to the fourth, multiplied by the length of the joist. It's gonna be kind of tricky. I need to understand all of this detail. It needs to be smaller or equal to 2/3 of the floor width. Now, what is the floor width? Not also clear on this. So I'm gonna have here a big question mark on this, right? I don't know what this mean by floor width. Also, I'm not clear on this. And also this one, what does this say sub j? C sub j. All right, I'm gonna go here to the next one. Here's the same equation again. And it says, usually this C sub j is gonna be equal to 2 for any interior beams. So I'm gonna say this here applies to interior beams. So So if you have interior beam, C sub j is going to be equal to 2. If you have exterior one, which is parallel to the edge of the concrete deck, it's going to be equal to 1. So understand this. Means if you have any steel beam and you have two concrete, like you have the deck on both sides of the beam, you're going to be taking this Cj is going to be equal to 2. So this is going to be here number of deck flanges or number of sides with concrete deck. So if you have it only one side, which means it's going to be like an edge beam, use C of 1. If you have it interior, it's going to be C of 2. So this is going to be simple. Now I understand this. So okay, it says here ES and EC, I understand both of these two, right? We are familiar with this, the modulus plus testing. We understand it for concrete and for steel. Now here's the new part. The joist or the beam transformed moment of inertia. Beam transformed moment of inertia. What does it mean by that? I understand transformed moment of inertia. But it says here you need to find it per unit width. Width of what? You're going to say you're going to have a few beam here running next to each other, right? With the spacing of S. So what you need to do is to find out transformed moment of inertia for each beam and then divide by the spacing. Does this make sense? Spacing between what? Between beams. So what you're trying to do is to find out the average moment of inertia for the beam in the beam direction itself. It's going to be also transformed, don't forget that, which means that you need to take the concrete, convert it into steel. So what is DS? I'm going to say DS is going to be the slab transformed moment of inertia per unit width. This is going to be the same thing as if you are taking here 1 foot of the metal deck and the concrete on the top of it and try to find out the transformed moment of inertia of that concrete in steel. I'm not going to say here you need to divide by spacing because you have taken already a foot. It's going to be a strip. And you can determine it from this equation here. So they give an equation for it. It says here 12 times DE, the effective depth of the concrete deck, cubed, divided by 12, divided by N. And I guess you guys know N is going to be the modular ratio. You remember the modular ratio? Relationship between ES and EC? But now this is going to be dynamic modular ratio, which is a little bit different from the modular ratio that you're aware of. The one that you know of, this N is going to be equal to ES divided by EC. And usually we cut off the fraction. We just take the fraction out of our equation. Here it's going to be a little bit different. We're going to call it dynamic modular ratio. So I'm trying to understand this more. Why it says here 12? And this D here is going to be an inch, right? So 12 actually is going to be the width. This is going to be like B. So the original equation is BH cubed. You guys remember this equation? Divided by 12. This is exactly what I'm looking at. It's going to be moment of inertia of the concrete slab. H is going to be here D sub E, effective depth of the concrete. And 12 is going to be this 12 inches for the width B because you are taking here a foot. Divide by 12, I understand divide by 12 because it's going to be BH cubed divided by 12 constant. And then also divide by N. Why? Because you'd like to find the transformed slab moment of inertia. Okay, what is this effective depth? Let's say, let me look here at this for quick. I'm going to skip one slide. I'm going to go back to it. Here is a standard concrete deck over steel deck. And then also you have the steel beam. So it looks like this. So let's say when we say W3 plus 3 1/4 inch of lightweight concrete. W3 means the deck thickness, the metal deck thickness is going to be 3 inches plus 3 1/4 inch. It means the slab thickness is going to be 3 1/4 inch. Or sometimes we say W3 plus 4.5 inch of concrete. So the deck thickness is going to be 3 inches and the slab itself is going to be 4.5. Now D sub E, you understand that the deck is going to be going up and down in the flutes. So in this case, you're going to be taking 1/2 of the deck thickness and add it to the slab thickness. And with that, we're going to be calling this D sub E. So how much is D sub E? What's your understanding for D sub E? D sub E is going to be equal to the slab thickness plus 1/2 of the deck. So we're kind of averaging it and we call this D effective, which makes sense. Gonna go back here to that slide and say, okay, now I need to find out the moment of inertia for the slab. Divide this by the moment of inertia per foot for the beam. Okay, now I did the slab and I have done the beam, but also I need to find out what n value should I use here in my analysis. It says here's dynamic modular ratio. In the past, for the static modular ratio, we used to say ES divided by EC. In the dynamic, we're going to be adding here a factor of 1.35. So here's a new change. Don't just take the old n that you're used to. No, now it's going to be ES divided by 1.35 E sub C. In here, I have definition for moment of inertia for the beam, length of the beam or the span, the spacing, which means a beam to a beam, the spacing, and effective depth, which is explained right here in the slide. So I guess we're clear on whatever that we're looking here at. So are we good with the 3 slides? We understand this, we understand these factors, we understand the C value is getting either 2 or 1. It means number of sides for a steel beam, number of deck sides. DS is going to be the moment of inertia for 1 foot of the slab. That's why we divide here, we are just taking 12 inch. And DJ is going to be transform moment of inertia for the steel beam itself. And L sub J is going to be the beam span. The only thing that I'm not clear about here is going to be the floor width. What is the floor width? Definition of floor width. Let's say that I have a building and the floor plan here is 300 feet by 500 feet. How much is the floor width? Is this a 300 feet or 500 feet? Usually we feel the width is going to be like the 300 feet, but this is incorrect. We need to have more information to determine this. I'm going to be coming to it very soon. So, okay, how about for the girder? I said for the girder, I'm going to have, for the girder panel mode, when you do the girder, don't forget, you're going to be doing the beam, and then you're going to be doing the girder, and then combine with your equation. I'm going to have very similar equation to the previous one. Here it says BJ is going to be for the joist. It's going to be CJ. And then you have DS and DJ. So, okay. How about for the girder? It's going to be CG. So I'm going to have C sub G. Very similar to the other equation. And instead, I'm going to have supporting member, which is a joist, divided by D sub G, which is the girder. If I may go here back a few slides, it was DS by DJ. It was the slab to the steel beam. In this equation, is going to be the steel beam to the steel girder. And again, multiplied by the length of the girder. Let's say it should be 2/3 of, or it should be within 2/3 of the floor length, not the floor width. So I'm not very clear on that. It says here, how about this C sub J? C sub J, if I may take you back also here, C sub J, we have 2 values, 2 or 1. Depends on number of sides of the deck, composite, or number of sides around the beam that you see a metal deck. In here, it says here, C sub G is going to be either 1.6 or 1.8. But I'm not very clear why it is going to be 1.6, 1.8. I'm just going to go here to the next slide. And this is going to be one of the added slides that I put there. This is here a standard beam to beam connection. So this is going to be here the girder, and this is going to be the steel beam. So, okay, good. This is very good detail. Now, this beam is connected to the girder through a shear tab. If you remember the connection design that we have done in the connection slide set or lecture, we have something very similar to this, right? So we're going to have this plate, and this plate is welded to the girder. And you're going to have bolts, and this beam is going to get attached to this plate with these bolts. Now, how about here? What is the difference between this system and this system? If you look here at this system, you see here the beam or the joist is sitting on the top of the girder. So this beam here is restraining the top flange, and it is not attached at all to the web of the steel girder. But in here, I have direct connection between the steel beam and between the girder web. So here I'm kind of restraining this girder when it vibrates, that this web here is not going to be going right and left. It's not going to be freely going up and down, but it's going to be here restrained with the steel beam connection. So in a case like this, C sub G is going to be equal to 1.8. And as it says here, for girders, supporting beams connected to the girder web. This is going to be the girder web, right? This little thing. And here it says C sub G is going to be 1.6 for girders supporting joists or beams connected to the top flange of the girder. So now I understand this. So let me go back here one slide. I guess now I'm clear about this C sub G 1.6 and 1.8. And the picture is going to be a perfect illustration for it. So okay, now I understand this factor. I understand the span of the girder. Now what is DJ? DJ, I understand DJ. This is going to be the same one I've used here. Look at this. This is going to be D sub J, right? The joist or the beam transfer moment of inertia per foot when you take it and divide by the spacing between beams. So I'm clear on this. Now the new thing is going to be D sub G. What is D sub G? It's going to be the girder transfer moment of inertia per width. So we need to work on this a little bit. We're going to be looking at more details of what we're looking at. So okay, I'm going to skip this for a second. Just look at this one here. Here's a floor with some framing on it. Now, where is the floor length, generally speaking? Where is the length of the beam or the length of the floor? Yeah, say length of the floor is going to be this dimension from here to there, right? Direction of the beam. The width is going to be this direction here. So look at this. How much is this from here to there? Yeah, say 105. How about this here from here to there? It's going to be 120. So actually, the width of this floor is longer than the length of the floor. Because usually the very common feeling, once you see this, you're going to say length is going to be the longer dimension of the plan. This is what we are used to. But according to this design guideline, the length is going to be parallel to the direction of the beam. And the width is going to be length, or is going to be perpendicular to the beam itself, not the girders. So, okay. So this is going to be here the length, it's going to be the width. Let's say that I'm working on this bay here. I'm trying to do the vibration analysis for bay A. I'm going to say this A is going to be the same as this, same as this. Why? Because when you look here at the building width, where is the building width for A, for this panel A? You got to say the building width for panel A is going to be from this column to this column. It's then going to be the entire width, right? This is going to be the width of the building. When it comes to panel A, when panel A is vibrating up and down, look at number of beams that you're cutting through. You say, I'm cutting through all of these beams. And the concrete deck is running from here to there, right? For this section of the building. So this panel A and panel A, building width is going to be from here to there. How about the building length? You can say building length for A is going to be from here to there. This is going to be 105. Okay, this is about A. How about C? If you're doing here analysis for any one of these, C or C or C, right? Where's the length of the building for C? I'm going to say length is going to be from here to there. How about width? I'm going to say width is going to be from here to there, right? For C, it's going to be 120, and the length is going to be 105. So, okay, this applies for this C, for this C, for this C. Yeah, if you look at this one here, where's the width? You're going to say, here's the width. Where's the length? This is going to be the total length. How about in B? I'm just looking at this side here. What's going to happen? This is going to be different because the length is 70 feet and the width is 120. Now I understand if I'm doing some analysis, I need to do separate analysis for A, for panel A, and then panel B, and then panel C. Order is not critical, but what I'm trying to say is the width for A is going to be from here to there. This why this can be the same as this, same as this. How about this one? Can it be the same as A? I'm going to say no, because the width is going to be larger. How about this B? Can I say B is going to be the same as this C? I say no, because the length of the building is going to be from here to there for the purpose of this analysis. Okay. This is exactly what you can see it here in this small table. It says for A, the floor width is going to be 90 and the length is going to be 105. Yes, here's the floor width. It's going to be 90 times 105. This exactly includes, this table here includes exactly what I was working on right now. And I was trying to find out the width of the building and the length of the building for each one of these panels. So you have here the panel or the bay, and then you have the width, and then you have the length. Any questions on this issue about building length, building width?
Is this how buildings will always be cut up and everything or divided?
Yeah, usually it's going to be divided. So you should expect like maybe an opening, big opening for stairs or so. So I'd like to ask, let me ask here again, Mahim, because I'd like to do the grades for the evaluation points. So I'm gonna ask Mahim here. If I'm gonna go here to this panel, see this panel?
Yes, sir.
How much is the building width here and how much is the building length?
Sir, the building width would be 13 divided by...
The building width for this one.
Sir, the building width for this panel is 30 feet.
30 feet?
For the whole panel C, yes. And the building length is 35 feet.
Okay. All right, thank you. Anyone else? Anyone else? Anyone wants to be evaluated with this question? Bakri, are you there? Bakri?
Yeah, I'm right here.
All right. Can you help me with finding out the length and width for this panel?
Yes, I believe I can.
Okay.
90 by 70.
When you say here 90 by 70, is this the building width or the bay width and length?
The bay width and length. Well,
Okay.
3 bays of C.
Okay, no, I'm just looking for this bay here. How much is the length and width for this bay? Just looking at one bay. How much is the length of this bay and the width of this bay?
35 by 30.
Very good. All right. How about the building length when I'm working on this panel and the building width?
Same thing because it's the bay, right? That's what it is. The bay encapsulates that specific section.
Not really. All right, so let me repeat this again, and please give me your attention. I've noticed here that that some people are not giving enough attention. If you like to do analysis on this bay, all right, I'm just gonna pick here a bay. Forget that it's called here A. I'd like to do here analysis on this bay. Are you guys with me? Are you listening,
Yes,
or
Yes, Professor.
you are somewhere else?
Here.
If I'd like here to do analysis for this bay, and they ask you about the building width and length, the building width is gonna be this dimension from here to there. And the building length is gonna be this dimension from here to there. So the building length is gonna be parallel to the beam itself, and the building width is gonna be perpendicular to it. So in this case, for this panel or this bay, the length is gonna be 105 and the width is gonna be 90 feet. Are we good?
Yes,
Yes.
Professor.
Okay.
Yes.
Let me move to another bay. I'm gonna say, let me check here this bay. I am looking here for my analysis. What's gonna be the building length and the building width? So where's the building length? You say building length is gonna be from here to there, right? This is gonna be the building length. When I do analysis for this bay, and the building width is gonna be from here to there. Now, how much is the width? You can say 120, and the building length is gonna be 70 feet. Are we good now?
Yes, Professor.
Yes. No.
Yep.
Yes, Professor.
All right. Now let me go back to Maheen. Maheen, help me with this bay. Forget about the name of it. How much is the length of the building if I'd like to do analysis on this bay?
The length will be 35 plus 25, 70
The building,
feet.
70 feet for the length. How
Yes,
about
sir.
the width?
The width will be 120 feet.
120. Thank you. All right. I'm going to go back to Bakri. Are you there?
Yep, still alive.
All right. Okay. I'd like here to work on this panel. When I
Yes.
work on this panel here, I'd like to find out the building width and length. How much is the building length here?
90.
The building length is 90?
Oh, sorry. No, 35 times 3. 105.
105. Okay.
Yeah,
How about the
okay.
width of the building?
120.
All right. Thank you.
Yes, you're welcome.
And I guess here you can see the summary here. For each one of this A base or panel, the width is going to be from here to there, and the length is going to be from here to there. This is why this is going to be the same as this, as this. This is why they are labeled this way. Okay. Now I'm looking here for the effective width, which was the issue. In my analysis here, I was just looking at it and say, tough equation. I don't know where it's coming from. I'm trying to understand it, but I'm not clear. We said here that the effective width of the panel, of this panel here, effective width of the panel. So this slide is about the effective width of the panel. Which panel? For the joist panel, for the beam panel, and the girder panel. So I'm gonna say, how about the length of the joist itself? Length of the beam. I'm gonna say, length of the beam is gonna be like from here to there, right? If you like to do length of this beam, is gonna be from here to there. So it depends which beam that you're working on when it comes to analysis. Length of the beam is gonna be from here to there. This is gonna be the length of the beam. How about the width of the beam panel? I'm gonna say, is it important to you? I'm gonna say yes. Let me take you back to understand the importance of this B. I'm gonna take you back here to this slide, number 21. It says the weight that you need to use in your analysis. Someone's gonna say, which analysis? I'm gonna say, for this guy here. You remember for this calculation, we said that the promise gave was Fn and W. How would you find out this W? I said that the weight that you need to use is gonna be equal to the weight of the panel, effective weight of the panel, as it says here, effective panel weight is gonna be equal to some uniform load times the length of the panel, which means the length of the member itself, multiplied by the width of the panel. So how much is the width of the panel? Is this gonna be from one beam to another beam? I said no. Actually, we have a way of doing it. Now moving forward, I'm gonna say, look at this, the effective width of the panel. So if you like to find out W, which means the total weight that used here for the beam panel is gonna be equal to W, uniform weight, times the length of the beam, L sub J, if you like, right? Multiplied by B effective, which B is gonna be BJ. So where's this BJ? It's gonna be this one here. What is BJ? It's gonna be some width of a few beams. It's not gonna be just for one beam. And it needs to be less than 2/3 of the floor width. So if I'm working on this panel here, how much is the floor width? Can someone help me? The floor width.
The floor width is 120 feet.
Exactly, 120. So the maximum B sub J width, right, is gonna be equal to 2/3 of 120. Are we good? Now you understand the floor width here in this case?
Yes,
So in
sir.
this equation, it says usually less than or equal 2/3 of the floor width. So if you are working in panel A, the floor width is 90. 2/3 of this is going to be 60 feet. So the maximum width for this, the limit is going to be here equal to 60 feet. While if you like to apply it for this width, if you are working on B or C, right, in any one of these two, you're going to see here the floor width is 120. 2/3 of 120 is going to be how much? It's going to be 90. So the maximum is going to be 90 feet. This guy set here the limit for you. So you need to understand the building width and length for each one of these locations to be able to find out 2/3 of this floor width. So this can set the limit for you. If I'd like to work here on this beam, you see I'm working on this beam. I'm very specific. I'm working on this beam here. How much is this L sub j for this beam? Let me go to Basil.
Yes, Professor.
Yes. How much is the length, this L sub j, for this beam here that I'm working on?
That would be the 105.
I'm not looking for the bending length. I'm looking for the beam length. I'm saying how much is this L sub j, which is the beam length? How much is this beam length, in your opinion?
Just the 35 feet.
Okay, it's gonna be 35 feet. Good. How about this C sub j? What factor should I use here for C sub j?
2,
Why 2?
because it's an interior beam.
Yeah, interior beam. How about if you work on this beam? C
1.
sub j is gonna be what? Exactly, it's gonna be 1. How about the width of the building? If I'm working on this beam, how much is the width of the building?
Width of the building would be from, so mm, that would be the
Floor
one
width.
would be- oh, floor width. 120,
120. All right,
the whole thing.
right. How about DS and DJ? Where'd you get this from, Bassem? Okay. Do we have tables for them, or do we do calculations, or what?
So from the whatever it's called, the guidelines, we
Yes.
get DS would be for the slab.
Yes.
Um,
And DJ.
DJ would be for the beam.
And what is this D? D is what? Is this the depth or
No,
the
it
moment of inertia?
represents moment of inertia divided by
The spacing.
length.
Yeah,
the
no, by the
spacing,
spacing.
or
From one beam to another beam. This is what we call here S. So you divide by this. Thank you,
yes.
Bassem. Very good. Thank you. So okay. Now it seems that when I do here the analysis, vibration analysis, I'm not gonna be just taking one beam. I need to take a few beams altogether, because this B sub j is gonna be based on maybe a few beams altogether. And this is gonna be determined based on this equation. Okay, now it makes sense. It's gonna be a ratio of the beam span. You see this? L sub j, you take a ratio of this L sub j. So let's say if L sub j is gonna be equal to 35 feet, and this factor C sub j times this is gonna be equal, let's say, to 0.6. You're gonna say now the width is gonna be 0.6 times 35 feet, or 0.5 times 35 feet. So talking about maybe 18 feet, 19 feet, something in this range. Compare it with 2/3 of 120, which means how much? Let's say 2/3 of 120. How much is that? 80 feet?
80.
Yeah, about 80 feet. Yes. So it's gonna be less than 80 feet, then you go ahead and use 18 feet. The spacing here, how much is the spacing between two beams here? How much is S, the spacing between two beams? Can anyone help me with this? From here to there.
30 divided by 4.
It's gonna be 30 feet divided by 4. It's gonna be 7.5. Which means if you take
7.5.
here 18.5 feet, or let's say 20 feet, you're gonna be capturing here 3 beams to work together, right? So they're gonna be going up and down together. This is what it means by the panel. So in this case, the panel is gonna be taking a few beams together with the concrete slab and say, this is gonna be the weight, is gonna be working with our moment of inertia to find out the amplification. And of course, before that, you find out what? The frequency of the beam panel. We say, okay, how about the girder? about this equation here. What does it mean by that? Look at this equation. This equation here, you're going to have this C sub G. You remember the 1.6 versus 1.8? If you have the beam connected to the girder through the web from the top of the flange, say, okay, yeah. So there's going to be some factor multiplied by L sub G. What is L sub G? If I'm working on this girder, how much is L sub G? I'd like to talk to Elizabeth. Go ahead, Elizabeth.
The LG would be the length of the girder.
Yeah, which is how much?
Well, that would be 30 because it'd be across the way.
Correct. How about if I'm working on this girder? How much is this?
That's 30 as well.
30 feet. Thank you very much. Thank you. So it's going to be a fraction or a factor, because sometimes it can be longer. It's going to be a factor multiplied by the length of the girder. And this factor is going to be equal to 1.6 or 1.8. It depends on the girder and the connection, right? Connection of the beam to the girder. You're going to come up with this coefficient. And then you need to find out the moment of inertia, dj for the beam divided by moment of inertia for the girder. And with that, you can do also this girder panel analysis. What do you mean by do girder panel analysis? So I'm going to take you back, and please stay with me, stay focused. I'm going to go back here and show you a few slides. I'm going to say when you do here F sub n is going to be equal to 0.18 square root of G over delta, you're doing it for what? Now we do this once for the beam, and then you do it once, as it says here, for the beam or the joist, and then you do it once for the girder. And then after that, you do the combined effect. You can't do this unless you know the weight, which weight you're going to be using. And also in this equation here, you need to find out the combined weight between girder panel and beam panel, right? So this weight is going to be important. So, okay. This is why you need to have the length and the width for the panel. So, okay. Let's say that not 100% clear. Of course, an example, and if I have the steps, it's going to make my life much easier. Okay, good. They also give you some more information here. They say the effective concrete slab is going to be how much? You say you take minimum of 40% of L sub J, which this L sub J, what's L sub J? The beam or the joist length, and the spacing S. So, okay, this is going to be the effective concrete slab width. And when it comes here to effective concrete slab width, when it comes to girder, why do I need this? You say, because you need to find out here the moment of inertia of what? You're going to say of the slab and the beam all together. So if you like to find out here, if you want to find out dj, how would you find it, dj? I recommend just doing it for one beam and the concrete slab within a distance of S. I'm going to take you back here to composite beam design. In composite beam design, if you recall, we said you're going to be taking S or L over 4. You remember the span divided by 4? Yes?
Yes, Professor.
Find out the effective width. So in here, to find out the effective width for the concrete slab, that's going to be working with the beam or the joist, you have some guidelines. It says here, take 40% of the span of the beam or take the spacing X, the spacing S. You take the smaller value of the two. In the past, when we were doing composite analysis, we were taking what? S or, anyone remembers? 25% of the beam length. Am I correct? Because it says here's the beam length divided by 4, right or wrong? Yes?
Yes.
Okay, good. So in here, we have different rules. This is what I'm trying to tell you here. You have different rules. Even for the N, if you remember the N, the modular ratio, we have the static modular ratio that we used to use. N is going to be equal to ES divided by EC. Here we have it, N dynamic modular ratio is going to be equal to ES divided by 1.35 EC. I'm going to take you back to it so that you remember. You see this? ES divided by 1.35 EC. This is what you call here dynamic modular ratio. So dynamic modular ratio is going to be completely different from static modular ratio. The static one is going to be just ES divided by EC, and here is going to be ES divided by 1.35 E sub C. So the factors that you are used to they're going to be slightly different in this case. So, okay, understand this. Moving forward. So now I understand exactly how much concrete
Professor?
I'm going to be using. Yes.
For different type of panels, for example, for panel B, A, and C, they have different lengths and widths. So when we calculate differently for them, like we will calculate separately for each panel, right?
Yeah. If you are doing just, you know, in real life, in real application, you need also, you know, this. Usually you're going to have a software. With this software, you're going to place all the columns, right? And then you're going to build this. It's going to be like visual or maybe imported from a CAD system. And then after that, all what you need to do is just to click on the beam and the software is going to be doing the vibration analysis for you. So if you like to do vibration analysis for the entire floor, you just hit the button. You're going to have maybe 200 pages out of calculation just for the vibration analysis of the floor system, right? How about for our course here? What should I do? For our course here, I'm going to be asking you to do vibration analysis for one beam or for one bay. That's it. I cannot ask you to do for all of them because here in this case is also simple, right? Because all the spans are the same and all the column spacing or the girder length is going to be the same. The girder span is also the same. So they made it here very simple. And you still have 3 cases, 1, 2, and 3 cases that you need to work on. But for us, we need just to pick one beam as going to be enough for your work. Okay?
Okay.
All right. How about the effective panel weight? Now we said the panel weight needs to be the combined weight. How can I do here the combined weight? Because look at this. When you look here at the width, you say this is going to be the panel or the beam panel, right? This is going to be the beam panel. I'm going to take it here aside. And I'll put it right here. You can see this is going to be the beam panel. How about the girder panel? I'm going to say this is the girder panel. Here's the girder, right? Going to be taken. Maybe this is going to be the girder panel. So the weight of the girder panel is going to be maybe this weight. About the width I'm going to bring it from here. How about the length? It's going to be, let's say, roughly, it's going to be the girder length. How about this area here? What is that? I'm going to say this here is going to be the panel area. Length by width. Where the width is coming from? From here. Where's the length? It's going to be the beam length. How do you combine them to do this combined mode? Should you just add this to this? You cannot add this two weight to each other. It doesn't work this way. You need to combine them in a certain way. So what this guideline says, the combined weight or the total weight is going to be equal to. Look here, you find out deflection of the beam and deflection of the girder. And then you find out total deflection. And then you find out participation factor. So you say d delta sub j, which means deflection of the beam, divided by total deflection of the beam and the girder. Multiplied by what? By the weight or effective weight of the beam panel. Which means if you take this factor here, add it to this factor here, you're going to have a total of 1.0. So let's say deflection of the joist was equal to, I'm going to put here through some numerical example. I'm going to say deflection delta sub j equals to 1 inch, let's say. Delta for the girder, I'm going to say for G, I'm going to put it uppercase, right? It's going to be equal to, let's say, half an inch. The weight for the J, which means for the beam panel, is equal to, let me throw there a number, I'm going to say 500 pounds. And the weight for the girder, let's say about 800 pounds. How much is the effective weight, total weight? Let's say effective weight is going to be equal to what? First, let's find out this participation factor. What is this participation factor for the joist first? We're going to see here a total of 1.5, correct? Total deflection, in this case, is going to be how much? Can someone help me? Total deflection is going to be 1.5 inch, correct? How
Yes.
about deflection of the joist divided by 1.5 inch? Deflection of the joist is going to be 1 inch divided by 1.5. How much is this? Let's say it's going to be equal to how much? 2/3. Correct? So this participation factor for the panel weight of the beam is going to be equal to 2/3. And this participation factor for the girder panel is going to be equal to what? 1/2 inch divided by 1.5 inch is going to be equal to 1/3. So what do you learn from here? This plus this is going to be equal to 1, correct? And in this case, this W is going to be equal to what? It's going to be equal to the weight of the beam panel. I'm going to say 500 multiplied by 2/3, correct? I'm going to be taking 2/3 of this plus 800 multiplied by 1/3. Are you guys following? Make sense or no? Or repeat?
Yes, makes sense.
Okay. So this is going to be a very simple equation. I have here this participation factor. It's going to be how much deflection the joist is going to be seeing or looking at or experiencing when you compare to the deflection of the beam and the girder. And same thing here, deflection of the girder compared to the total deflection of the beam and the girder. And each one of this participation factor is just multiplied by the effective weight of the beam panel and the girder panel. And with that, you have the final W that you're going to be using in your analysis. Which analysis? I'm going to say the analysis that says AP divided by G. You remember this AP divided by G? Let me take you back. We're on slide 32. Let me go back to this slide. This equation here. It's going to be the actual W that you need to use in your analysis. When you do the combined analysis, this needs to be the W that you need to use. This can be this way because you combine here the effect of the joist and the girder. So we're going to go back here to 32. Now we understand this equation, have an idea how it works. And then it says here, for some cases, you do your analysis, and then you see here that the BJ, what is BJ? Let me go back here to this, just to be sure that you understand it. How much is BJ here? You say BJ is going to be from here to there, right? Usually BJ, usually in lots of cases, is going to be smaller than the girder length, correct?
Yes.
Okay. How about if this BJ is larger than the girder width, the girder length? What's going to happen? Now, this system here wants to vibrate. What is stopping it from vibrating? What's helping you out? I'm going to say what's helping me is going to be these two columns. This panel, when it vibrates, is going to be vibrating only in this direction. The beam is going to be going up and down, but not the entire width, because I have a problem here with these two columns. It's going to be stopping the vibration. It's going to be resisting the vibration. So the effect of the girder is going to get reduced. You guys agree? Yes, kind of.
Yes.
Okay. So the code recognizes this issue, not the code. It's going to be the design guideline. And they're thinking here, in a case like this, when the girder span, L sub G, is smaller than the joist panel width, so this when the panel width is larger than the span of the girder, you can reduce the deflection that you just calculate out for the girder. By what ratio? By the ratio of the girder length divided by the panel beam width, or the beam panel width. And they said you're going to have a range from 0.5 to 1. So the question is, if I did my analysis here and find out that L sub G divided by B sub J is going to be equal to 0.2, what should I use? It's going to be 0.5. How about if the span of the girder is going to be larger than the beam panel width, which means this factor here, when you do it, is going to be more than 1. Should I do it more than 1? You can say no. It's not going to happen, because in this case, just take the girder length and take delta G, delta sub G as is. Don't try to reduce it or increase it in this case. Okay. Now, do you have this procedure or algorithm or list of steps? Do you have steps that you need to do? I'm going to say yes. This design guideline, they include the steps for everything that you need to do. So if you are doing an example or a homework or work on your project, you just need to follow the steps here. So great, this is gonna be so simple, especially also when we have an example. It says number one, you need to work with the slab, which makes sense. Okay, work with the slab. What do you need to do here with the slab? Say we need to find out this dynamic, I'm gonna say the dynamic modular ratio. And this is gonna be so simple, right? You know about this.
Yes.
And also you need to find out the effective depth of the slab. You need to take the slab plus 1/2 of the metal deck. So if you say here W3 is gonna be 1.5 inch that you added to the concrete slab itself. And then after that, also you need to find out the moment of inertia for the slab, which is ds, right? You know this ds. Where is this at? It's gonna be right here. You see this, determine ds for the slab or the deck using this equation. So fine. After this, you need to work on the beam panel. Beam panel or joist panel, they're the same. You need to find out this I sub j. And this says, if you have a truss, and this is a beam, right? Because in many cases, the system is gonna be trusses supported by girders. You're gonna say, where's this at? Remember, we're at slide here 34. I'm gonna go back and look at some detail, like in here. What do you have here? You have an open web joist, or you have a truss. This looks like a truss. It's not a beam. That's why they call this a joist. And supported by the girder. But here you have a beam supported by the girder. So what they say, if you have a truss, you go to this section, right? If you have an open web joist, you go to this section. So there's certain guidelines. I'm not gonna be working on trusses or joists. I'm gonna be working on just steel beams. It's gonna be composite beams. So forget about this, but there's certain guidelines for it and how to do the moment of inertia for it. And this says here, figure out W of J. What is this W of J lowercase? It's gonna be uniform weight on like the dead load that you have calculated out. Also, it may include some permanent life load. So it depends on your analysis. If you're running a software, usually it says what percentage of the life load that you'd like to include when it comes to vibration analysis. Or how many, let's say, pound per square foot that you'd like to include out of the life load. Some people would put 10 PSF, 20 PSF. They say, usually we're gonna have people there. When you're talking about vibration, I'd like to include maybe 20 PSF. Because if there is no life load, what vibration are you talking about? If there is no life load and you have only dead load, and let's say at night time and all offices are closed, in this case, you're gonna say, well, there is no life load. Why do you care about vibrations? You care about vibration when you have some life load in there. People moving or something there, or maybe furniture. You cannot just assume that you have zero life load. Usually you're gonna be adding a little bit of some life load.
Sir, can we take this life load from the table in the CBC code?
No.
Like we used
You
to
don't take
take.
it. No. It's going to be based on practice and it's going to be based on some recommended values. This is not according to the code. You're not talking here about the occupancy life load. No, it is not.
Okay.
All right. And then it says here, find out deflection of the beam. I guess we are aware of this equation. We know how to use it. But when it comes to this moment of inertia, it's going to be which moment of inertia? It's going to be this transforming moment of inertia. After you do deflection, you do the frequency with this equation. Yeah, simple equation. Now you have the moment of inertia for the slab, and then you can find out the moment of inertia for the beam. And usually you just take the spacing. You just take dj is gonna be I of the j divided by s. Is it okay? After that, you find out the effective width of the beam. What's the effective width of the beam panel? It's okay, it's gonna be Cj if you have two sides or one side, ds divided by dj to the quarter, and then multiply by the span of the beam. And this needs to be less than 2/3 of the floor width. I'm gonna take you back here. This is now slide 34. Take you back for quick. I'm gonna say, oh, it's gonna be this equation. So I need to run this equation. and check if it's gonna be less than 2/3 or equal 2/3 of the floor width. If you're working on C, it's gonna be the floor width from here to there. It's gonna be very important to identify the floor width when you do some analysis. So, okay, I guess everything here looks okay. And then it says here, when you calculate this W of J for the panel, for the beam panel, it says if you have continuity in the beams, use 1.5. In our case, we don't have that. If the joist bottom chord are extended, use 1.3. I don't have that. So I don't have this factor here. So just use this. All right. How about the girder? I guess in the girder, you're going to be doing the same thing. You have this IG and the width of the slab. I'm going to go back here a few slides. The width of the slab is taken from where? I'm going to say, oh, yeah, this is here to find out the effective width of the concrete slab when you do this IJ or I sub G for the moment of inertia. And after you do it, you divide by the spacing between beams. Okay, the same thing. Effective width of the slab when it comes to the girder. I have this equation for it. It's going to be minimum. You have the side, right side, and left side. Okay, and after you do the moment of inertia, you divide by the spacing between girders, which means the span of the beam. Okay. So what do you do after this? You do deflection. Deflection, then you do frequency. And then you do D sub G, moment of inertia divided by L sub G. And of course, you'll find out the width. And then you understand if you have shear connected, like our standard beams, or you have on the top. On the top is going to be 1.8. And then what do you do after this? Forget about this 1.5. We don't have it. We don't have continuity between beams. So I'm not going to include this 1.5. Great. After this, you do the combined panel mode. Okay, combined panel mode. Now you have delta I, you have delta sub G, you have this 0.18 to find out Fn natural frequency for the entire system. And then you do the effective weight, like you combine it with this participation factor, if you like, right? What do you do after this? Now you have all the elements, you can figure out AP divided by G. What is AP again divided by G? It's going to be the acceleration of the system based on this equation, P sub 0, the 65 pounds. Now you have to the E to the negative 3.5 F sub n divided by beta. You have beta, you have here the floor system is going to be 1%. You have partitions, you have ducts and ceiling and all of that. And you divide by the weight. Which weight is going to be this weight here? Whatever value that you get here, if you have an office, you compare it with 0.5%. If you are close to 0.5%, I'm going to say maybe 0.499, you're good. Just call it 0.5. Any questions? Yes? No? All right. Example. The example here is very detailed. They give you a girder, some steel beams. They give you here is going to be paper office. What is the implication of paper office? Is going to be 1%
It will contain
for the beta.
pads.
Yeah, the beta is going to be 1%. It says assumed life load of 11 pieces. You just need to add it there. And then, of course, I understand that life load is going to be what? It's going to be 50, the occupancy. This is what you designed for. But this is the expected life load to be there in almost all cases, right? This is going to be the additional life load that I need to include when it comes to analysis for vibration only. It says there is ceiling and mechanical equipment. It's going to be also add some beta. Superimposed dead load. This is going to be the additional dead load. This is going to be 4 PSF. And then it says the spandrel girder is supported by exterior cladding for vibration. Okay. The building is 5 bays in the east-west direction. So they give you here some description, right? They say 5 bays in the east-west and 3 bays in the north-south. Okay. So in this direction here, it's going to be how much? It says here 5 bays and 3 bays. Beams are connected to the girder web, like our standard. So how much is the CJ factor? It says it's going to be right here. Shear is going to be like this. It's going to be 1.8 factor. So we're going to have less vibration. They give you here slab thickness is gonna be 5 1/4, 2 inch for this. So when you do the slab thickness, it's gonna be 3/4 plus 1 inch for the effective slab depth. And then they say also it's gonna be lightweight, 110 PCF, so that you figure out E sub C. And what else? Concrete strength is gonna be 4 KSI. The deck itself is gonna be 2 PSF. So it's giving you all the information you need. And you see, say also STM A992, which means F sub Y is gonna be equal to 50 KSI. Okay, good. Again, we're gonna be following the same steps that was provided to us here. Slab, joist, and then you have the girder, and then combined effect, and then you find the AP divided by G. So it's gonna be fun when you go through this. All right. So I want you here, and also you have here quick plan view that I developed for it, right? For the beam length and width. All the beams are running in this direction. Remember this. So this is gonna be the beam length or the floor length. It's gonna be 105. And the width is gonna be 150. It's gonna be from here to there. So all the beams are running like this, right? This is gonna be the direction of the beams. I'll let you go for now. And my request to you guys here, if you please complete this example to the end, so that next time when we are working on it, we can run a little bit quicker and faster. All right?
Yes, Professor.
Is everybody here?
Yes.
Is everybody
Yes,
available?
Professor.
Let me check. I have here,
Hello, Professor, I'm here.
yes. I have here 27 people in this meeting, right? Okay. 27 people meaning what? It means that I
26
have
students
everybody
and
available. This includes me. So we have 26 people plus the teacher. So we have here, everybody's available here. So I want to be sure that everybody's listening here to me. Are you guys listening?
Yes.
Is everybody
Yes.
on?
Yes.
Yes.
Okay, I'd like please unmute.
Yes.
I don't want you to miss this and say, oh, I was there, but I didn't hear you. It never happened. I didn't hear it. I don't know what happened. The voice was not working. I didn't hear you. Over this weekend, you're gonna have a quiz. It is something that I want you guys to go through with Proctoria. It should be a simple quiz. So I don't have here a homework for you, and instead I'm gonna have a quiz. The quiz should take about, it should take about maybe half an hour to 45 minutes. And once you're done with it, you need also to do it through the website. So I'm gonna give you enough time for it. So let's say the quiz is gonna be taken, let's say, just for sake of discussion, it's gonna be like an hour. Is everybody listening to me and hearing me?
Yes.
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 Everyone, please
Yes.
unmute your microphone. I'd like to see all microphones
Yes.
unmuted.
Yep.
Yes.
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 I have Diana.
Yeah.
Are you there? And Kevin, if your microphone is muted, you're not there. You didn't hear me. And it's gonna be up to you. Diana, are you there?
Yes.
Okay, good. Everybody's unmuted now. Good. All right. So what's gonna happen? Let's say the time is gonna be really like an hour. This is gonna be the worst case for when I'm working. I just take my time. It's gonna take me maybe about an hour. This is for myself, right? So I'm gonna give you here a window of 4 hours. All right, you're gonna have a big window of time, right? It's gonna be 4 hours that you can work on. As long as you work, you're gonna have the computer is gonna be videotaping you, right? Proctoria is gonna be watching you. So you cannot really take 4 hours to solve it. It doesn't make any sense unless you have that much time and you'd like to be in front of the computer and work. It's gonna be up to you. But my advice to you, once this quiz is available to you, you start to take it. I know lots of people, you're gonna be waiting after 3 hours. And then all of a sudden you're gonna say, okay, now let me work on it. and it's gonna take you 1 hour, and then at the end, time is gonna be short, time is tight, I cannot do it, I cannot upload it, the system just shut me off, I don't know what to do. And I'm not gonna be there. There's not gonna be any Zoom meeting. It's gonna be you and the computer and Proctoria. So that you guys, you have fun all together, right? You, the computer and Proctoria. It's gonna be all the fun, I guess. So my advice to you again, please start work on it once you have it there. It's gonna be assigned to you. It's gonna be open on Saturday. I'm planning to do it Saturday, let's say between 12 p.m. and 4 p.m. Is this good for everyone?
You said Saturday, right?
Saturday?
Yes. So, yeah, it's gonna be over the weekend.
Oh,
Is
that's-
everybody now? I'd like to see all microphones. If you have any issues with 12 p.m. to 4 p.m. on Saturday, let me know. Diana?
I can't do that. I'll be moving, so I won't have a computer all day Saturday or Sunday.
So what day you prefer to have your quiz, Kelsey?
I could do Friday, either
Friday.
tomorrow night or
Great.
Friday
No,
night.
no, Friday. Let's stay here with Friday. From what time to what time? Any time?
I get off work at 5, so after that.
Great. I'm gonna say between 6 p.m. Friday to 10 p.m. Is everybody okay with this? Friday?
Yes.
Yes.
Yeah,
that's better.
Yeah, I'd like to see all microphones, please. Diana and Jonathan.
Yes, that's good with me, Professor.
Yeah.
Okay.
Okay, so Friday 6 to 10. Okay.
Friday 6 to 10. You're gonna see here the quiz, and you need to be ready, and you need just to take it. And don't keep it to the end of the duration of this 4 hours. Don't put yourself in trouble.
Will this cover everything we've learned from now, or is this
Yeah.
based on this lecture?
Yeah, it's gonna be everything. Also, it's gonna be like open notes, but do not communicate with anyone else.
Is it
Yes.
everything even with the midterm or just after the midterm?
Everything. And the structure is still design only.
Okay.
So nothing about concrete design, nothing about traffic design, right? For analysis. It's
So
gonna be only in the
everything from
structure
day
steel
one
design.
of this semester till now.
What?
Everything
Huh?
from day one of this semester till now is included in the quiz, right?
Yes. Yeah. And as I said, it shouldn't take more than half an hour. You shouldn't have a problem here with uploading. You cannot claim that the computer system was slow. All right?
Okay, Professor.
Any questions?
Sir, just to make sure, it's on Friday 6 p.m. to 10 p.m. and everything till now is included in the quiz, right?
Yes. It's gonna be a simple quiz. It's not gonna be a tough one.
Okay.
Okay.
You're muted.
Any questions?
Nope, sounds good.
Nope.
All right. You guys have a good night.
All right. Thank you,
Thank you,
Professor.
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 Thank you.
Professor.